Hello. So today we'll be going over the stability of differential equations by Erica Wang. So what is differential equation stability? A differential equation is said to have stability when, for any initial conditions, the solutions of the equation are bounded, meaning they don't increase or decrease infinitesimally. A differential equation is said to have asymptotic stability when, for any initial conditions, the solutions of the equation are bounded and eventually approach zero. The initial conditions of the equation do not especially affect the end behavior. So basically what you're going to be seeing is this is like a graph of the solutions of an equation, and like you see all these different lines, all these different solutions, they all start from like different places with different initial conditions, and they all are bounded and eventually approach zero. X equals 0. So now we've gone over stable and asymptotically stable equations. So what about unstable equations? An unstable equation is basically not stable. The solutions or trajectories move away from each other rather than approaching zero. As you can see here, this is stable and this is unstable. Unstable nearby trajectories move away. They're like all moving away from each other. And the stable nearby trajectories have move closer. Or at least don't move away. That's the derivative equation. dx over dt equals f of x. The stability of equilibria of a differential equation. So stable, unstable. As you can see, this right here is stable, but it's not like asymptotically stable because this line right here isn't zero, although the trajectories are all approaching one specific value and they're like all moving together, they are not approaching zero. Yeah. Unstable. They're like starting off and then they move away from each other instead of towards. That's the difference between stable and unstable equations. And then this is the stability at a point. You can see this is unstable, while this is stable. Okay, more about unstable equations. At the top of the graph, this graph right here depicts an unstable differential equation. You can see they are like moving away from each other. Some are moving up, some are moving down, some are just like staying there. The bottom of the graph depicts a stable equation. You can see like they start off from like different spots, different initial conditions, then they all move up or down all the way to one specific spot line, aka -2. The stable equation, is not asymptotically stable since the solutions approach -2 instead of 0. Now, if this spot like moved up 2 spots and this line were over here and they were all approaching 0, then there would be asymptotically stable, but it doesn't, so it's not. It's just plain stable. And so now that we know what stability of equations is, here we'll go over the importance/use of differential equation stability. So the stability of equations is used very widely in real-world problems and has significant effects in nearly all situations involving equations. So basically, when you use a mathematical model to model a physical problem, there will always be error. when you're gathering like the initial conditions, whether it be human error, instrument error, or random error. Therefore, there will always be slight deviations from the mathematical model. The initial conditions will always be different, and thus if the equation were unstable, such minor deviations in the initial conditions would result in large variations in solutions, which will compromise the ability of the mathematical model to accurately predict the outcomes of the problems. Therefore, you basically won't be able to use the mathematical model because it wouldn't be reliable. Small errors would greatly affect the result, which could, if depending on the situation, could put like, say you like building a bridge or something that could like put a lot of people in danger. So to be able to safely and accurately use mathematical models, the equations must be stable. That's why knowing the stability of an equation is very important. Okay, so this part doesn't really mention stability. It's just an example of a mathematical model. Specifically, here we model the dynamics between pathogen and immune system cells, which are also known as memory T cells. And like here, it's just a graph modeling that using a mathematical model. As you can see, as time increases, the tumor P cells don't really change, but the memory T cells increase until like roughly around 50, where they like slow down and taper to like a constant. So that's just an example of a mathematical model. Okay, now the Routh-Hurwitz Criterion. The Routh-Hurwitz stability criterion is a statement determining whether or not an equation is stable. According to the Routh-Hurwitz stability criterion, any equation or system can be stable if and only if all the roots of the first column have the same sign. If the roots of the first column do not all have the same sign, or if there is a sign change, then the number of sign changes in the first column is equal to the number of roots of the equation with positive real parts. So this is just like a way to calculate mathematically, like by hand, the stability of whether or not a differential equation is stable. Okay. The Routh-Hurwitz criterion provides a shortcut to determine whether or not an equation is stable, because originally to determine whether or not the equation is stable, you had to like graph it, try to see whether the solutions all came together in the previous graphs. But with the Routh-Hurwitz criterion, you don't need to solve the equation and then graph it to find the stability of the equation. You could just like calculate it mathematically, like as you can see, B1, C1, B2, D1. So I will just make sure they all have the same sign, and then the equation is stable. Unfortunately, there are some drawbacks to Routh-Hurwitz criterion. First, the criterion is only applicable for a linear system. Second, and most importantly, the calculation of the stability of an equation using the Routh-Hurwitz criterion is inefficient and takes too much time by hand. Therefore, I have written Maple procedures to demonstrate the stability of differential equations and systems of differential equations in a time-friendly and cost-efficient way. Okay. By using Maple programming, Maple procedures. Here I use the powerful Maple function dsolve-numeric to write the procedures to calculate the stability of differential equations or systems of differential equations. So these procedures just basically provide a very efficient and easy, it doesn't really cost anything, a way to determine whether a differential equation is stable or not. First, many conditions are picked randomly. You can see there's a a wide range of conditions here. Like this is like 5. This is a 4, 4, 2, 1, 0, no 2, no 5. Many initial conditions. These initial value problems are then solved and solutions are graphed on the same graph. So like every line represents a different solution, and they're like all graphed, and you can see that they are equal to point x equals 0. Again, each different colored line, green, yellow, red, blue, purple. Each different colored line represents a different initial condition. As you can see, all lines equal to 0, indicating that the equation is asymptotically stable. This method is based on numerical approach, so the equation can be either linear or nonlinear. Remember, the Routh-Hurwitz criterion could only be used on linear equations, while this can be either linear or nonlinear. Okay, we may run the procedure many times. If all the solutions approach 0, we can believe that the equation is asymptotically stable. This is not a theoretical proof because it can be used as verifications, or it can be used to get an idea about the stability of an equation. It can also be useful for teaching and learning differential equations of system theory. Here I have written 2 procedures. One procedure is to determine the stability of differential equations, while the second procedure is to determine the stability of systems of equations. Here's an example. Yeah, I've been using this graph. The stability of the name of the procedure is stability. The first argument of the procedure is D. The second argument of the procedure is the equation, and the third argument is the range of the independent variable. And that was the graph. And here, it's just a code. This procedure shows graphs of a differential equation with many random initial conditions. The first argument is the differential equation. The second argument is the order of the differential equation. And the third argument is the range of the graphs. Yeah, I did not include the graphs in this PowerPoint. So we'll just, how do you do this? We'll just X out. And for and then we'll just head on over to this document, which is yeah. And then here, I think that's a graph in the PowerPoint, and then here are the other graphs. You can see this one too is stable because it all goes to one point. It's perfectly stable. Now it goes to 0. And yeah, just small graphs. This one is not stable because it's unstable at all. It all heads off. The trajectories all head off to a wide range of values. This one is stable. All the lines are stable to 0. Unstable. This is really weird, but yeah. I suppose if this graph were to be like extended and now be centered on the zero, it would to be stable. This is stable. This is unstable. Yeah, they don't approach zero. It's not asymptotically stable. This is very beautiful and it is stable. Asymptotically stable. All the line trajectories of the solutions approach zero as the independent variable increases. Okay. And that's it about the stability of differential equations. Thank you for listening, and it was a pleasure to have you.